is day one of Unit 6, Exponential Functions. So we've done a lot of different things now. We've gotten into linear equations, solving those equations, linear inequalities, solving those inequalities, graphing both intersection points, systems, and now we're going to take a look at a different type of function. Okay, there's three types of functions typically that we have. We have linear, exponential, and quadratic. So this unit is going to be about exponential functions. Day one, what is the difference between linear and exponential functions? Well, let's go ahead and fill out this table of values. It doesn't give us what the function is. It doesn't say y equals, I don't know, 4x minus 2 or something like that. But it does give us a table. And we can fill this out. We have x and we have f of x. And recall that f of x just means y. Okay? And obviously this is x. So we can fill this out. Let's look at the x values from 0 to 1 to 2 to 3 to 4 to 5. I guess you can figure out what's going to come next. 6 and 7. Okay. Now we need to figure out what's going to come next after 23. Let's see if we can find some kind of pattern. We're going to go from -5 to 7. Well, how much did we increase by? I think we're going to go up by 7 here. Okay. And now from 2 to 9, well, we're also going up by 7. 9 to 16, we're going up by 7. 16 to 23, we're going up by 7. So each time for the y values, we're going up by 7. So, guessing we're going to keep the pattern going. 23 add 7, I get 30. 30 add 7. And then 37 add 7 is going to be 44. So look at this. We're just adding 7 each time. Right? And over here, key components. What is the pattern of the table? Well, we add 7 to each f of x. We're adding 7 to each f of x, right? Let's go ahead and actually plot this. Go ahead and do this, guys. You should be able to graph these at this point. 0, -5. 1, 2. 2, 9. And I actually can't do anything more. These are the 3 points, but I can connect them with my line, which I will do. Okay, something like that. And I can't label this, we don't know what it is. Let's go back to the key components. Here is this function graph from the table of values. Pattern was to add 7 to each f of x, right? Now, what that is, adding 7 to each f of x. See how this is the pattern? Well, anytime we add or subtract a certain number of numbers, and it's the same, that is known as what we call in algebra. This whole thing is known as a common difference. Okay, this is your common difference when we add or subtract the same number in a table of values, and that number is not going to change. In this case, it's 7, so 7 is my common difference. Now, back to the key components. Type of function. Well, this is a linear function. Right, it's a straight line. Rate of change. What does rate of change mean? Well, again, for linear functions, we always said that the rate of change was the slope, at least for linear functions. Okay, the rate of change is the slope. And in this case, it's not changing at all, right? The rate of change is going to be 7 over 1. That's my slope. And it's going to be the same throughout the graph. Okay? So type of function is linear. The rate of change for linear functions is the slope, which is 7 over 1, up 7 to the right 1. And that's going to be the same throughout the graph. Okay. Number 2. Got my x values. So again, I can fill in. I know what the x values are going to be. It's going to be 0, 1, 2, 3, 4, 5, 6, 7. But now, what is the pattern going on here? Going from 1 to 2, 2 to 4, 4 to 8. Okay, so we're not adding by a common number anymore, because we add 1 here, add 2 here, add 4 here. So that's not common. So maybe we shouldn't think about adding or subtracting. Let's switch to maybe multiplication. What did I multiply by 1 to get to 2? Well, I multiply by 2. To get from 2 to 4, I'm multiplying by 2. To get from 4 to 8, I'm multiplying by 2. Continue this process down. 8 times 2, 16. 16 times 2 is 32. 32 times 2 is 64. And 64 times 2 is 128. Okay? So again, what is the pattern of this table? Over here at key components, what is my pattern here? The new pattern here is we're multiply by 2. All right, multiplying by 2. As opposed to up here, we were adding 7. So now we're multiplying by 2. Well, let's now graph this piece. Let's graph 0, 1. That's going to be here. 1, 2 over 1 up 2. 2, 4. 3, 8. 4, 5. 4, 16. And then 5, 32. I'm not going to be able to graph that. But I do have my graph now. If you think about this, I can't really draw a straight line from here. If I drew a straight line, it's not going to work, right? It's going to have to be curved some way, shape, or form. So let me try and connect these dots with my pen. Right? Something like that. Maybe not the best depiction, but it looks something like this, right? Now, just like we did up here, I think we can already tell this is not the same as a linear function, right? It's getting, without giving too much away, it's getting exponentially larger at a super fast rate, right? From 4 to 5, we went up 16, right? And then from 5 to 6, we're going to go up 32. It's just increasing at a ridiculous rate. Now, what we call this up here, we added 7 each time. It was the same thing every time. We add 7. Okay, that was add or subtraction. That's where the common difference comes in. Now, down here, we're multiplying by 2. Right, we're multiplying by 2. So in this case, this is what's known as your common ratio. Okay? Recall what a ratio is. A ratio is just pretty much a division, right? Either 1 to 2, you could write like this. You could write 1 to 2, or you could write it as 1 over 2. So this is division here, right? Well, division, we know, goes hand in hand with multiplication. So this is a good way to remember whether it's a common ratio, which is division or multiplication, over here, or whether it's common difference. We add or subtract, and the word difference can kind of help us with that. Subtraction goes with addition, addition goes with subtraction. This is common difference. So, what kind of function is this? This is no longer a linear function, but this is an exponential function. Right? So what's the difference in the key components from a linear function to an exponential function? Well, the pattern, we added 7 here, either add or subtract. For exponential, we're either going to multiply or divide. And what is the rate of change? For short, ROC. Well, we can't really pinpoint what is the exact rate of change. It's different from each interval. From here, we're going from 1 to 2, from 2 to 4, from 4 to 8, to 8 to 16. It's not constant. Right? It's not a constant. It's not a constant rate of change. It's different for each interval. It is different for each interval. For example, let's say we're looking at between x equals 0 and x equals 1. Right? Well, the rate of change here was just 1. It was positive 1. We went from 1 to 2. So the rate of change was 1 over 1. Now let's look at from 2 to 3, from when x equals 2 to x equals 3. Okay, what was the rate of change there from 2 to 3? It's 4. 4 to 8, the rate of change is 4 now. So these are just two examples to show that the rate of change is different for each interval for exponential functions. It's not the same rate of change. It's different each time. Okay? Key components of exponential functions. Get down any notes you need, pause, rewind, and let's go on to the next page. All right, let's get down distinct characteristics of these. What is a distinct characteristic of a linear function? Well, for a linear function, table pattern shows either add or subtract by the same number. We either add or subtract by the same number, and this pattern is called your common difference. All right, and that is represented just by the letter D. That is your common difference. And the rate of change is constant. It's constant. AKA, it's the same between intervals. It doesn't change. For linear functions, it's always constant between whether you're going from 3 to 2, 2 to 1, 1 to 0. Okay, it's going to be the same. Exponential functions. The pattern shows either multiply or divide by the same number. Right? And this pattern, as we said on the front page, is called a common ratio. And that is represented just by the letter R. Okay, so common difference is represented by the letter D. Common ratio, if you have a highlighter, I would use it now, is represented by the letter R. And again, as we said on the front page, the rate of change for exponential functions is different between intervals. It's not the same. Let's look at number 3. Use the function. It's giving us a function now, right? It's giving us g of x equals 2x minus 3. It wants us to use this function to fill in the table below and graph. Well, hopefully I remind you on Monday that you will take home the calculators So you should have your calculator with you, because now we need to start getting really good with our calculators. They're lifesavers in essence. If I want to figure out what is going in for g of x here, which again, g of x is just another way of saying y. So this is still my x, this is my y. How am I figuring out what's going in here? Well, we want to use our calculator. Okay. Star, use your calculator to fill in the tables. Okay, and the way we're going to do that, okay, I can't really show you a calculator, but I can show you the steps. The first step, right, the first step is to hit y equals on the calculator in the top left corner. Second step, you want to type into y1. Make sure everything else is cleared out. You want to type in what the function is. Well, in this case, it's 2x minus 3. It's not too hard. Third step, hopefully, ideally we know what to do here. To find a table of values, we hit second, and then we hit graph, and that will bring up our table of values that we can fill in. Okay? So, do that now. And you should get a nice table of values that you can fill in starting at x equals negative 3. So you should see that your y is now at negative 3, we have negative 9. Negative 2, we have negative 7. Negative 5. Negative 3. Negative 1. Positive 1. Positive 3. Right? Fill in the table below and graph. Okay, we filled in the table. Let's graph it now. So at negative 3, negative 9, we have a point. Negative 2, negative 7, we have a point. Negative 1, negative 5, we have a point. 0, negative 3, 1, negative 1, 2, positive 1, 3, 3. Again, connect that with a nice line. Nice straight line here, going all the way through. Now it gives us what the function is. Anytime we have a function, make sure that you label that line. Make it complete. This is g of x equals 2x minus 3. Okay, what type of function is this and why? Well, we can definitely see this is a linear function. Why is this a linear function? Use specific words. Look at what it's going up or down by in the y column here. I'm going down by negative 2 each time. I'm subtracting 2 every time. And when I say subtracting 2, I clearly mean adding 2. Hopefully you guys caught that. It is late. So make that switch. Because negative 9 plus 2 will give me negative 7. We're adding 2 to each piece here. Right? Add 2, add 2, add 2, add 2. Right? So if we're adding or subtracting by the same number, right, that is what is known as our common difference. So why do we know that this is a linear function? Because we have a common difference of 2. What is the domain of this function? Again, domain is the x values, right? Left to right, here's my x-axis. Left to right is my domain. Well, the arrows, which I should have down here, tell me this is going on forever all the way to the left and all the way to the right forever. So again, it's going from negative infinity to positive infinity. Infinities always have parentheses. What is the range? My y values. Again, remember range, like vocal range, low to high. Well, y values all the way down. That arrow tells me it's going down forever to negative infinity. And the arrow up tells me it's going all the way up to positive infinity and parentheses. What is the rate of change? The ROC. Well, we know for linear functions, the rate of change is always the same. And we see that our common difference is 2. So my rate of change is just 2 over 1. It's constant. I have a constant rate of change. Very indicative of linear functions. Okay? All right, last one. Try to make this quick. Use the function g of x equals 1/2 x to fill in the table below and graph. Okay, so again, let's go to y equals, right, and fill in our table of values. So we got to clear y1 and put in 1/2 to the x power. So go ahead and do that. Pause the video if you need to. I'm going to start filling in the table. Okay, so at -3, we should get positive 8. And 4, 2, 1, 0.5, 0.25, 0.125. And then go ahead and graph this. -3, 8, -2, 4, -1, 2, 0, 1, 1.5, it's about there. 2.25, it's about there. 3.125. Okay, so something like that, right? If I want to connect these, look like that, right? Nice little arrows, and this, of course, is g of x equals 1/2 to the x. So, hopefully, we can see this is not a linear function. We can't connect this with a straight line, right? So this has to be an exponential function. Look, it's getting exponentially lower. We always work from left to right, like we're reading a book, reading a sentence. We look left to right. Well, I'm starting up pretty high on the left, and as I keep going right, I'm getting really low, right? And it's getting super close to 0, but it's not touching. If I kept going with this, it's never going to touch 0. Right? What type of function is this? Exponential. Why is it exponential? Well, look at our table of values. Are we going down from -3 to -2? It's a rate of change of 4. -4. From -2 to -1, it's a rate of change of -2. Right there, it's different. It's not constant. Right? It's not the same number. So, if it's exponential, we know that it has to either be multiplying or dividing. So if you look here, everything is being divided by 2. Right? Divide by 2, divide by 2, divide by 2, okay, so on and so forth. So, if I'm dividing by 2, that's the same thing as multiplying by 1/2, right? 8 times 1/2 would give me 4. 8 divided by 2 would give me 4. This is the same exact thing. These two equal. So, instead of having a common difference now, I'm having a common ratio of 1/2. Okay? What is the domain? Well, again, these arrows tell me a lot. Domain is my x values. These arrows tell me it's going all the way up forever in the x to the left and all the way to the right. So, again, my domain is going from -infinity positive infinity. The range, it's a little bit different. Look here. My lowest y value, well, it looks like it's 0, but is it ever going to touch 0? Think about that. It's just going straight on, getting ever closer to 0. If I look at my table of values here, it's getting ever closer to 0, but never touching it. So my lowest value is going to be from 0 all the way up to infinity. And again, it's not a bracket because it's not going to hit 0. Last piece. What is the rate of change? Well, the rate of change, we don't know. It's not constant. It's different for every interval. In other words, if I go from x equals -3 to x equals -2, my rate of change here, let's take a look, is -4. I'm going down from 8 to 4, so my rate of change is -4 over 1. Then, if I go from x equals -1 to x equals 0, my rate of change, let's take a look, from 2 to 1. It's -1 now, -1 over 1. Therefore, it's not constant. This tells me it's not a linear function. It's different for every interval. Okay? You guys need to take a look back at, pause it, rewind it, do whatever you got to do. That's the end of